That must go there. Yeah, that does.
That's it.
Gulliver's laws. That must go there.
That's right. That must go there.
Royal Institution Christmas Lectures. Lecture 4, Lilliput and Brobdingnag since the Industrial Revolution.
Thank you. I have brought along this time the latest edition of Gulliver, a paperback that you can buy in the shops. I hope those of you who have not read the complete work will do so. It's a fascinating book. I was looking in it for more up-to-date news of Lilliput and Brobdingnag since Gulliver's visit. But alas, not another word occurred. The latest word seems to be from Gulliver's visit. And quite a lot must have happened between that time and this. There's very little doubt of that. The only place I found any reference to the Lilliputians since Gulliver has been in this book by a splendid and very well-known British author, Mr. T.H. White. The book is called Mistress Masham's Repose, and tells the story, the following imaginative story. Here's the book. It's really very beautiful. The book concerns a Mistress Masham's Repose, which is a small island in the middle of a small pond on a great deserted estate. And a small girl, Maria, a young girl, discovers that on that island for 200 years and more, there have been living a colony of exiled Lilliputians who got there because when Gulliver was picked up, if you read the book, you will learn that Gulliver carried with him a few small sheep. And these sheep were very valuable and could be exhibited at the fairs and demanded a great price. Therefore, the captain who picked up Gulliver from his small boat adrift in the sea knew where he had picked Gulliver up. And then himself went back the following year, found these Lilliputians on the coast, scooped up a dozen men and women, 6 inches high, and brought them to England, where he displayed them in the fairs. But of course, they were very clever people, and very concerned, and he was just a fair-going man. He drank a little bit heavily, perhaps. And one night, they escaped. And they made their way to this tiny island in the middle of a pond, where no one ever came because of the deserted estate. It was a very small place, and the Repose was this old summer house of the 18th century in which they lived as a kind of secret city. And the small girl falls upon that by chance. And of course she's amazed to see these Lilliputians, and they too are amazed and frightened. There are now 1,000 or more of them, natural increase, and they're afraid of being discovered and put upon by men, big men. She holds their secret and befriends them. A fascinating book. Again, that same beautiful mixture of what I would like to call science fiction of the best sort, and also an account of the human mind and character as seen from little people and big people. And a very nice thing is this. Maria, to make peace with them, finally after a great quarrel is made up, decides to have a splendid gift for them. And she and her advisor, who is a scholarly old professor, argue about the gift. And this is their argument. She had gone through a tussle with the professor about choosing the gift. He, with his giant's obsession about choosing small things for small people, had wanted to buy an old-fashioned sweet, which is sometimes used on cakes, called Hundreds and Thousands. Do you know them? Yes. They are tiny pellets of hard sugar, colored pink or white or blue. Maria had insisted on full-size chocolates. Which would you prefer, then? A hard piece of sugar about the size of a toffee apple, or a chocolate cream the size of a pram? It's a very nice lesson in putting yourself in other people's places. Big people should not get the smallest things they can make for little people, because the smallest things that we can make will be ordinary objects for little people. But we should give them the largest things that we imagine they can possibly use. Not something too large for them, but something larger than they could easily make, ever. And of course, a box full of chocolates the size of a pram is exactly a wonderful gift for a town of Lilliputians. But that's the only news we have concerning anything of Lilliput since the 18th century. But we know, and of course that was not of Lilliput itself, but only of a colony of exiles. So they had no chance to change with Lilliput. We know that Lilliput must have changed a great deal since then, because certainly London changed. Here's a map of London in Swift's time, in Gulliver's time, the 18th century. It extended, this built-up area extended from Wapping Steps right across the river, along the river, very little on the south, not very far north from the river. And we in the Royal Institution here are over here, about in there. The block of Bond Street is occupied by a great series of gardens and a beautiful estate. And just a little distance out here, we come to the countryside. That's very different from Mayfair and Regent Street and Oxford Street today. And you will see this again in the picture of modern London. Here is the rectangle shown in the 18th century map, and countryside all around the edges. And here is the outer circular in London today, with countryside coming in a little bit to the edges here. Notice how much bigger the area of London has become. So we are quite sure that the 18th century Lilliput is very different from the Lilliput of today. But alas, no news has come to us. So in what I would like to say today, I want to discuss the nature of life in Lilliput, and also in the giant land, Brobdingnag, which is so hard to say that I shall often call it the giant's country, or the giant's land. Since the coming of the rise of technology and industry, which has made such a difference to our lives. Of course, this is only a fanciful way of asking ourselves how it is that our machinery, our technical civilization would work if we imagine it scaled down very small or scaled up very big. It's another study in scaling, such as we have had. Now, Gulliver, Swift's invention, Gulliver, was a little bit unclear about the technology that he found in Lilliput and in the giant's country. For example, he does not find gunpowder at all, though of course it was very well used in Europe, very much used in Europe for 200 years before his time. The three great early inventions which we learn about in history are printing, gunpowder, and the magnetic compass, all old inventions, all going back, I believe, to China originally, and all entering Europe slowly in the early Renaissance, late medieval times, and making their impact as time went on. And their culmination was perhaps the great age of discovery. Now, did the Lilliputians have these old inventions? I think they did. And we'll see in which respect. For example, consider printing. This is letterpress printing, the standard method of printing with raised shapes on paper. Notice these magnificent large letters, and above them, a tiny Gulliver. That's the scale at which we can do letterpress today. There's no difficulty with doing such letterpress. We have easily able in our own presses with our own resources to make very small and very large letter blocks. For example, here is the large wooden block G from which a Gulliver, for Gulliver's Laws, could be printed very large. And if we can do that, large and small, with a factor much greater than 12 between these, we can be quite sure there's no great difficulty in making old-fashioned printing, letterpress printing. I'm not talking about photographic methods or rotary presses or all the modern times, just the 17th and 18th century style and older, could easily have been available to them. And I think in the book it looks as though Lilliput had it, but it's not clear that the giants had it. But I think they both could have had it and probably had it very soon, and printing works extremely well. It is, however, true that the eyes of little people are not as good as Gulliver reports. He talks of them threading invisible needles with invisible thread. But I'm not so sure that that would have worked, because their eyes had to be 1/12 the diameter of our eyes, and the pupil 1/12 the diameter of our pupils. And it seems easy enough to scale down the optical instrument, but of course they are not scaling down the internal structure of light. And as you know, light has a wavelength, and this we do not change, and therefore their optical instruments probably did not work as well as ours. Indeed, it is very likely that the Lilliputians had to use, I have made the calculation, they have probably used type, not with an elegant, fine I, such as that italic I you might imagine, but rather a nice block letter like that, because while they could see small letters, I don't think they resolved the fine details as well as we did. Their eyes are too small. Indeed, if you look at living animals today, you will find that Lilliputian animals, animals of mouse-like size, 6 inches long, have quite conspicuously large eyes, large in proportion to ours. And that is because the light does not scale, and therefore evolution has arranged it that they should see quite well and not simply keep the eye in the same proportion. Optical instruments, which are perhaps the greatest scientific accomplishments of the 17th century, making the revolution, the telescope and the microscope, were not very good, therefore, for Lilliput. Here we have a normal-sized telescope of Gulliver's time, just such a telescope as Gulliver, after he had become a sea captain, might well have carried. A beautiful telescope which does work, though it's not in very good alignment today, and it has this wonderful folding vellum style and beautifully made ivory caps, and is altogether a fine 18th century instrument. Now, if I make that instrument 1/12 size, it will not work quite so well. And indeed, as you know, our optical instruments, our telescopes, to see great distances, are gigantic objects. Consider the great telescopes of California, the Mount Palomar telescope, 15, 18 feet diameter mirrors. Now, of course, that's gigantic for a Lilliputian. They will probably never be able to make it. Whereas the giant people, that's only about this size. Our 1.5 feet is 18 feet for the giants. And a 1.5 foot telescope, while not easy to make, is something which a very skilled amateur can make working all by himself. Therefore, even the amateur astronomers among the giants probably had superb views of the heavens. And since I am really an astronomer by trade, I would very much like to see the reports of the Brobdingnagian astronomers, because they must have really grand telescopes to work with, provided they can overcome the problem of scaling against weight, which is an engineering problem I hope some of you will think about. The microscope is a different matter. The microscope, which here is a microscope a little later than Gulliver's day, about 1740, it's very hard to make a microscope with very tiny lenses. It simply doesn't really work well. These lenses already are a couple of millimeters across. If you try to make it a 1/12 as large as that, you will not get good results. So I don't think that that Lilliputians found a very easy time to do microscopy, not as easy as the 17th century Londoners, for example, the marvelous work of Robert Hooke, who made this gigantic, splendid drawing of a flea in Micrographia, his famous and most popular book of that time. The Lilliputians could make microscopes, but microscopes were expensive and difficult objects for them to manufacture. Again, the giants, though they couldn't work to very small scale, could work to refined scale just as we can, and therefore I'm sure their microscopes were quite good. Now, the other inventions of the early times, as I mentioned, here is a Lilliputian compass. We have not had this compass specially made. This compass is a working contemporary compass actually used by Mr. Bill Coates, senior experimentalist here, who cares for our apparatus, when Mr. Coates was a paratrooper. Just imagine that during the Second World War and thereafter. And in fact, he promised at one occasion to jump from the top of the dome for us to demonstrate parachuting, but there wasn't enough room. Now, that compass works very well and is a perfectly reasonable Lilliputian compass. If I made it 12 times as big, I would have a compass very much like this fine old ship's compass, a little later than Gulliver's time, but not very much, about 1790. And you see compasses work quite well in these scales, and we have made a great big needle, which would be a small, tiny toy compass for the Brob people, for the giants, and it also works quite well. And if you calculate the weight upon the bearings and the strength of the magnetism that must go into a large needle, you'll find the two scale about in the same way, both going up with the volume of iron used. And therefore it's not difficult to make compasses on large and small scale. There's no question that all those people could have had magnetic compasses, though quite possibly they weren't much used to it because they didn't voyage, as we are told, very much at all. They couldn't voyage, of course, or we would have had visits from them before now. Thank you. I must say the large compass is much more sensitive to iron. That is, it's sensitive to iron nearby on its own scale. And therefore, the bigger the compass, the greater distance around you must clear the world of iron in order to have a good reading of the Earth's field. And that is, again, a kind of scaling. But again, the giant people would not have had any trouble doing that. On the other hand, gunpowder is a different matter. Have we our charge? Bill, let us try a little gunpowder out. Villainous stuff that it is. Here is a charge, not of gunpowder, but even of gun cotton, a somewhat more elegant explosive. This is a 2-gram charge, the equivalent of a big grenade for us, plus a detonator and wires which we have not weighed. And we will try exploding this charge in a sand pit to see what kind of a cratering it gives. Now, watch your step. We've tried that. We'll cover the camera monitor to keep it being filled with sand. Watch your step. The brave boys in the front row will keep clear. We've tested it several times, and I hope nothing will go wrong. But I want to demonstrate that gunpowder is explosives are fearful stuff. Now, remember, on the Lilliputian scale, that bucket of sand is a 12-foot green of sand, a golf green of sand. Watch what happens to it with a 1 or 2 pound charge. 3, 2, 1, fire! Oh, bad shot. That always happens in the explosive world. Thank you very much, Bill. Take care. Little people also had failures of explosive. That goes all the time. If you do the scaling, you will discover that the per unit weight of powder, the size of the charge and the size of the damaged region scale up together, because it is the amount of explosive energy that determines the amount of energy released into the outside world. It turns out, therefore, that the area of damage is somewhat smaller, 2.5 or 3 times smaller for us than for a given scaled weight of charge among them, and a couple of times larger for the giant people. So that the Lilliputians found explosives somewhat more dangerous than we do. In addition, they have more surface to volume, of course. You remember that. The smaller, the more surface per unit volume. The surfaces of structures are what are pushed by the shock wave, and there's more the strength is controlled by the pressing on the surface than the weight which holds it in place. So surface is a little more vulnerable for Lilliputians, and small objects are torn apart by scaled explosives more easily than with us. Therefore, the Lilliputians must have found gunpowder quite bad. It's a small effect, but a noticeable effect, a factor of a few. But more than that, guns were even more serious for them, because the work done by the powder goes into the speed of the bullet, the kinetic energy of the bullet. If I scale the mass of the bullet and the mass of the powder together, I get the same kinetic energy per unit mass. That means the same velocity. But if 2 bullets have the same velocity, they will go the same distance. It's true the area is just a little greater for the small bullet, but again, that's not a very big effect, factor of 2 or 3. So it turns out that Lilliputian guns then have a range, perhaps not 12 times the scaled range of our guns, but several times. So with small guns and small cannon, they could already shoot across cities and do great damage at a distance. They didn't have to wait until they could see the whites of the eyes of the regiment. And therefore, I think gunpowder must have caused wars to become more rapidly more terrible for the Lilliputians. Perhaps they were very wise, like the early Japanese, and made it illegal to fight with gunpowder. I hope that's the case. On the other hand, for the giants, it was not a revolution. Here, of course, is what a Lilliputian cannon would look like. We're not going to fire this cannon. I'm not sure it would stand a proper charge, proper scaled charge, but it's a handsome-looking object. It shows you the breech, the muzzle, the breech, the touch point, and the carriage which takes the recoil when we fire it off. And you can imagine little wars fought that way being more terrible than ours. The giants, on the other hand, the explosive effect is relatively small, and their cannon, since they had only about the range of our cannon for the scaled size, means that a cannon which had a few mile range for us, made 12 times as big in all dimensions, would fire a much heavier ball, which would of course do about the same damage to the much heavier structures of the giants, but it would only fire 1/12 as far. That's to say the same distance, but their distances are much larger. Therefore, a good-sized cannon would not even fire across their principal city. And so I don't think they worried much about cannon and gunpowder, and it was not a very important matter in case of war. Only the truly Brobdingnagian weapons that, alas, in our last decades have been developed among men of our size. Only then, when atomic explosives and rocketry became real, would modern weaponry mean a great deal to giants. Of course, we know that those are things that are on Brobdingnagian scale, and therefore this is what we might expect. Now, as to the other machinery of the early Industrial Revolution, the principal use of power was in looms and textile machinery, weaving, spinning machinery. Here is a real loom, a man-made loom for working, doing home weaving. My tie is also woven by hand. And you see how it makes the shed, and you can imagine the shuttle going across. Now, of course, there's a gigantic loom for Lilliputians for weaving blankets, I should think, or some large tapestries for the king, 8 or 10 feet wide. But it works perfectly well, coarse cloth for Lilliputians, and there's very little doubt, though I have not been able to study the scaling very well, there's very little doubt that you could do textile machinery with about the same success at the Lilliputian and the giant scale, with the appropriate size machinery. Thank you, Bill. And this is what we would expect. Machine tools are still more important property of the Industrial Revolution. We have here a Lilliputian machine tool, which our familiar expert machinist, Mr. Bruce Morris, will operate for us. And we've obtained it at great expense by importing it temporarily, not against sterling, from Lilliput. I think that's right. You watch it turn very nicely. There are the chips. Thank you very much, Bruce. I think everyone has seen how the chips fly from the work. Of course, that's not a Lilliputian machine at all. It is a man-made and very useful and very beautiful watchmaker's lathe, such as is used for fine work among us. It would be an 8-foot lathe in the big Lilliputian machine shops. And I think we can be quite clear that they, given the proper power, would have no trouble in doing machine tools and making that kind of industry. On the other hand, the operation of metallurgy, which is perhaps the most essential of all the new processes that were scaled up after the 18th century, is difficult on their scale, and it's not at all clear to me that they would be able to make it work, the Lilliputians. Because metallurgy, notice here is a steel mill, notice the man, notice the hot plate of steel come rolling across. Magnificent, beautiful sight. Thank you, I think that's enough for the film. Lilliputians have a hard time with that. Of course, it's quite easy for them to make the machinery, that isn't difficult, but the difficulty is to keep the heat in the work. Remember, heat is lost through the surface. Heat is held by the volume. With their greater surface and smaller volumes, I think they've had trouble keeping the steel hot enough to work for a good long time. I haven't studied that in detail, but I think that must be very likely the case. On the other hand, the big fellows would have no great trouble with heat. They'd have splendid time to work, but they would have trouble with the enormous weight of all the equipment, and it would be more expensive for them to do metallurgy. Probably it can be beaten. Probably new methods can be made, which we have not yet studied. I'd like to know what their engineering is like. Chemical engineering is another place, the chemical industry, the manufacture of all sorts of products, from fertilizers to polyethylene sheet. This is a place where scaling is urgently important and used every day by the actual designers of chemical equipment. Indeed, they very frequently make their first chemical plant on rather small scale and study it. Not that it behaves, they understand very well the laws of scaling, so they can go from small plant to large plant, from the operation of small plant, understand how the large plants will work. Not simply by multiplying all the numbers by the first, second, and third powers, by a detailed understanding of how it works. It works quite differently, of course, because you'll remember that chemical reactions very often involve, like cookery, mixing, taking heat in and out. Changes in mixing reactions of all sorts are very often surface properties, and the surface to volume ratio must be dealt with, even though it changes over the plant scale in a considerable degree. And that is a fascinating story. Electrical engineering is a still more complicated matter, perhaps, but we can do something about that, and we'll look a little bit at some electrical engineering matters. Lilliputian magnets. Let's consider magnets on the small scale. Magnets work quite well on the small scale. Here is this piece of magnetic plastic loaded with iron, even with magnets, and I have a bar magnet that will just about adhere to the slippery sheet. I'm not sure it will really do so. No, it doesn't quite. tends to slide down at that angle. If I break it apart, though, into two smaller magnets, the small one stays quite well. Again, the corners and edges and surface effects of magnets are quite important for their pooling power. And since I have more of that for the same load, per unit load, I managed to make permanent magnets very well on a small scale. And I think that means that permanent magnet engineering is extremely important for Lilliputians and very difficult for giants. For example, we too use permanent magnet engineering very nicely. Here is a motor. I think you see it spin. I'll try that again. A rapid spinner indeed, and a beautiful piece of Lilliputian engineering. Of course, it's man-made engineering, inexpensive motor, and the principal parts of it are this turning rotor, which comes out and spins, having a coil and an electromagnet that we can hardly do without. You must be able to turn it on and off to make it go round. You may think about that. But the rest of it, what stands still, is a little horseshoe permanent magnet, and you see I can pick up a nail very nicely with it. It's really a permanent magnet. Thank you. So again, as I say, permanent magnets are likely to be very well made by Lilliputians and very often used, but I don't think that they're made by giant people, and conversely, giant people use electromagnets a great deal, but we'll see in a moment that electromagnets work relatively poorly on the small scale. Yet think how all our rotating machinery, our driving machinery on large scale for us almost always depends upon electromagnets. In fact, you see this quite well among us too. The huge generator we showed the other day was a typical Brobdingnagian object, and it worked beautifully with electromagnets, great coils of that huge copper bar that we had. Let us look a little bit at the scaling of one piece of electrical apparatus. I don't want to spend a great deal of time, but a little time we can spend on this. Let us look a little bit at resistance measures as a function of scale. I want to remind you of how resistance works with scale, this simple operation of resistors. Here we have these two electrodes, and I think we have a couple of people who are going to work as circuits for us. Can we have a couple of volunteer circuits? Thank you very much. It is worthwhile first bringing the two electrodes together to show people what zero resistance looks like on the meter. Can you do that? Just touch them. And there the meter way over here shows zero resistance. Now pull them apart, but don't touch them. That is. Now then, they're way over at the other end. That's almost an infinite resistance, nothing but the air and the dry wood between them. So here is zero resistance. Here is a very high resistance. Now let's measure your circuit resistance if we can. Do you want to wet your hands? I think it will help the contact because it'll make the contact more uniform if the hands are always wet. There's only a tiny battery here. There's no danger of any kind. I turn the scale, and therefore I read about 4 on this scale, which is a good place to read. Now let's try you. Very good. And again, not very different, about 3. Slightly larger hands, I believe, and that makes the difference. Now that's 3 and 4. Suppose we make the circuit go all the way through, what would you expect to get? The circuit is being lengthened. And so I think you will add first the one resistance and then the other. These people are in series. Of course, there's also a little extra contact resistance, and the result indeed is about 6 or 7. That's very good. That's similar to the sum. On the other hand, let's make the 2 circuits. You will allow the circuit to travel, okay? And then you help her. See, now the circuit is going through both at once. Each one is helping. The circuit has been widened instead of lengthened, if you like, and now the result is less than either one. It's well under 2, as you see here in the meter. Thank you very much. Good circuitry. So we see that the circuit works in that fashion. And now let me just describe the scaling a little bit so it gets some numbers down. It's clear if I have a piece of wire like that or a piece of wire like that, this is shorter than this. This resistance should be greater than this resistance. So the resistance in ohms, say, is proportional to the length of the circuit, L. And if I double the length, I would expect to double the resistance, holding everything else equal. That's what we learned from the series connection. But what about the other connection, which people call shunt or parallel, where both circuits work at once? That corresponds to putting another line here, to widening it. And of course, if I make it in proportion wider, twice wider, I would expect to get less resistance due to having more available. And the less comes both because of making it wider this way, and also in 3 dimensions, making it wider going in and out of the board. So 2 powers of L come from that, and that part goes like L squared. So the overall result is like 1 over L. The resistance, 2 similar resistors, will have resistance in the proportion 1 over their characteristic size, a typical size. So a big resistor, a big piece of wire, will have a much smaller resistance than a small piece of similar wire made by 1 power of the size ratio. Now that means that as we make the sizes of coils of wire, say, smaller and smaller, so we make the coils have more resistance. On the other hand, the magnetic energy depends on the magnetic field. The magnetic field we see occupies the volume of a magnet. We've seen some indication for that. And in consequence, therefore, as you make smaller and smaller coils, they work less and less well. More of the energy is lost in resistance. Less of the energy is given to magnetism, and the coils at small scale work very much more poorly than coils at large scale, which is why the electromagnet does not work well. I think we'll just skip that. Let me then look at a few pieces of electrical equipment which we have made, which we human beings at our scale have made. I think you recognize them. This is a small radio. It's a Lilliputian table radio. I think it has the woman's hour.
And now that the January sales are in full swing, the talk comes as a timely warning.
Well, it's quite normal, and everyone understands a little radio like that can be made. Of course, it's not a Lilliputian table radio. It's a small transistor set of our own scale. And here it is, and you notice this fine, wound red coil. That is the coil, and that we don't like to make coils a great deal smaller than that. Indeed, if you look at an integrated circuit, and again I have an integrated circuit, which is the same one we saw the other day. There it is, an amplifier mounted in the head of a pin. If you look through such circuits, there's the circuit on the head of the pin. It really is there. If you look at the audio amplifier, many times, you'll look at many integrated circuits, you will never find a single coil. You will find resistances, yes. You'll find capacitors, yes. We remember we showed those the first lecture. And you'll find many transistors and clever devices of all kinds, but hardly any coils. Engineers don't like to make small coils because small coils are ineffective, exactly what the Lilliputians would have found. On the other hand, on big scale, I think they would work extremely well. Lighting is something very important for us, and also for Lilliputians. Lighting may work with a small lamp, of course, extremely well. Here's an electric torch, and you see it makes a fine beam, and though the battery is big, in Lilliputian scale, that's a floor lamp size. And here is a small mains-operated lamp, 12 volts, and it makes casts a small glow on my hand. If you calculate the power you need, you would expect the power would go, because of the inverse square law with light, like 1 over the square of the size of which you want the light to shine. So the power for a given amount of intensity, which the eye can pick up, will depend for Lilliputians about like the square. That will be 100 times less power than it is for us. That's fine. And that's what that lamp is. That's a fraction of a watt, which is about 100th of the kind of lamp that would illuminate a 10-foot room. It's illuminate a few-inch room instead of a few-foot room. But Lilliputians have a hard time making that much power because they would like to make the power more by the amount of coal or fuel they burn, which goes like the cube. And therefore it costs 10 times more for them to run their lamps, which I think is a burden. Perhaps not making it impossible, but it is a burden. Now you see how it goes. Every sort of engineering can be worked out, can be studied on many scales, in Lilliput and in Brobdingnag. And wherever you see it, it's fascinating to discover what kind of scaling law it follows. I would like to appeal to students of science and students of technology, to future technologists and scientists, and also to many of you whom I know are enthusiastic hobbyists who like to make small aircraft or small locomotives or small machines of many kinds, to consider not only the appearance the excellent appearance of the models you make, and not even the performance, how fast they go, how they can win races, but even more in detail, how the various parts fit one with another, how they scale from the point of view of real engineers. Imagine you're a Lilliputian engineer. How strong is the part that you make? How much does it weigh? Can it use the same material as human engineers? If not, how much does it cost in Lilliputian economics to substitute the other material which will do the job? We very rarely pay attention to that. And I think it would be a valuable exercise for students and for engineering societies and engineering colleges to study as one small investigation, which is good fun and very helpful, what I have called the scaling problems in all kinds of engineering. I've tried to do a little of it for the purpose of these lectures, but it's quite plain that human engineering, like that of Brobdingnag and Lilliput, is an exhausting and difficult subject to which thousands of ingenious minds and much cumulative knowledge have been applied over the years. And you can't expect to get to the bottom of all these machines, not just to make something that looks like it, not even make something that performs well, but something that in the inward sense has the right kind of scale and has carefully thought through how you would make an economical, efficient, small locomotive from a Lilliputian point of view, that is a subject matter which we're not quickly able to manage. And here I hope that many people who have these specialties at heart and have these interests and these ideas at their fingertips will help us out and help me out. Tell me if I've been wrong in some scales. I may well have been. I would be quite prepared to see that. And also elaborate much farther than I've been able to do in this brief account on how you can change everything with scale. Let us look at one particular device, which is a familiar sort of model device, very nicely made, again by Mr. Morris, this fine old overhead wire electric train. Give us a slow trip, Bill. Looking rather realistic. Slow to start, and gradually picking up speed, going down the line of some plain below the Alps, the German railroad model. And now let us return the train with her high performance showing. Back she goes. Thank you very much. Now this is a familiar model about a scale of 1 to 70 or 75. It looks splendid. I think in all detail the looks are pretty good, except that the overhead wire is about 4 or 5 times too large, too little resistance. It's been given a heavy wire to help the current. The power is dropped by about the right amount, about 70 cubed, below the real power of the real human-sized locomotive. The weight has dropped with that, so the power-to-weight ratio is about the same. But given the same power-to-weight ratio, and given the same friction on the tracks, and it's not much different, maybe a little bit different, the same proportionate friction, the coefficient is about the same, this train will show the same acceleration because it has scaled force because of the power being scaled, scaled mass because of the mass being scaled, and therefore the acceleration remains the same. Less force, of course, less mass, of course, and therefore the same acceleration. But the acceleration then is 50 times too great compared to the real train, because it's 70 times, distances are all 70 times smaller than usual. And that's why this train could, as you see, pick up and stop on a dime. No trouble at all for a model of that kind, but not at all like the real surging increase and slow decrease of the full-scale train. And that's what I have in mind when I say that I would like to see more engineering models and more discussion of the situation, which we try to simulate as closely as we can what would really happen in the small-scale world, and not merely make what to us are showy performances, which are interesting, but possibly not just the same thing we want. Now, I want to spend most of the rest of the time talking about one kind of engineering which is very far from Lilliput and very far from the 18th century, but a fascinating one. I choose it because one has to concentrate on something, and it's an interesting one, and it is one, moreover, which has been so well worked out in respect to scale that I had a relatively easy time to understand what the relationships were. I want to talk about flight. Remember, we talked something about bird flight at the end of the last hour, and now I want to talk about flight both of birds, but also of those most splendid kind of birds, men, who can fly with the aid of their minds as well as of their evolved non-wings, and talk a little bit about how that works. You will perhaps recall, and I should just repeat the result, that the power required for flight, if I consider similar flying objects, the power required for flight has very curious behavior. It goes like the product of the weight times the wing loading, the weight divided by the area of the supporting elements. Now mind you, this is assuming a uniform a scaled uniform shape, so that whatever wing design you fancy, whatever good kind of elegant curve you have made, you keep that curve on the appropriate scale. The different performances depend on the nature of that curve, but given one shape of wing, then I can scale it up and down, and for a considerable range anyhow, I don't have to worry about changing the shape. So if I have this result, I can translate this directly into weight if I remember that the area of a similar object goes like the square of the length. The weight goes like the cube of the length. So I can relate the area to the weight. And working that out, I get W to the 7/6 power. That means a power a little bit more than 1. 1 1/6, which is a very curious result that I never expected, but is in fact there. Now, if we have enough power so that comparing with one single object, and now of course we're going to drop the requirement of ideal similarity, we never get that way, just going to try to be approximately similar. If I drop that idea, I'm going to try one fit to one weight airplane that and one power amount that will fly, and then we can see whether objects will fly or not, depending whether they have more than the required power or less than the required power. I can fit the curve to one point. So I know the shape of the curve, but I don't know where on a graph that curve will come without more calculation, of course. That's necessary for the real engineer, the real designer. But in my case, all I've said, if I have this kind of multiplicative plot, this power of 10 plot, plotting the power up this way, and the weight this way, 1, 10, 100, 1,000, using whatever units I will eventually choose, then I know the shape of the curve. It's a straight line on this kind of paper that goes up a little faster than 1 for 1, a little more tilted. But whether it's there, or parallel there, that I don't know, because I have only a proportionality and no equation. The equation will tell me which one of these curves to pick out. So if I pick out any single flyer, I can then fit the curve, then the curve goes through that flyer. I can compare that with what power is available. Alan, could you come forward? I have the great pleasure of being able to present to you Mr. Alan Lassiere, who was one of the Southampton group and is one of the few men in the world who have been both pilot and engine. Very nice flight. It was a long time of hard work before you got in the air, I take it.
6 years, I'm afraid.
6 years. How many of you were working?
About half a dozen.
Half a dozen people. Aeronautical engineering students?
That's right.
Yes, well, that's what it takes. And there's a lot of design behind that,
yes,
as well as the hard pushing.
Which I didn't do.
I see. Have you been flying once or twice, though?
Yes, I have been flying,
yes,
but I was a backroom boy. Really.
I see. Very, very good. How is that work going on now? Are there still some groups working on it?
Oh, yes. The Hatfield group, which you saw short sequence on, they're still working. Their aircraft still flying. They're still developing it.
I see. Do you think that what is the measure of success that you would like to
Well, a prize
achieve?
was offered 10 years ago for the first people who could fly the figure of 8, around 2 points, half a mile apart. And that's not been won yet.
That's not been won yet. Do you think the second generation of aircraft have a chance of winning that?
Certainly.
Oh, very good. That's the spirit, and I hope somebody here may take part in the third generation that'll do perhaps a 10-mile course. Here's the kind of transmission that was in there. I think you noticed it. Notice the cycle pedals and this nicely made framework. How much does this whole mechanical transmission with the chain drive and the second chain drive going to clear the apparatus and going up into driving this pusher propeller, about how much does all this weigh?
About 30 pounds. The whole aircraft's about 130 pounds, a little less than a man's weight.
So you see, a man has to about double his weight. That's the best he can do in terms of wing loading. And with that, there's a good chance of flight. And as we have seen, real flight, just not quite up to the mark set for the prize. But I think the real prize already been won in the sense of the understanding and the fact that you did get off the ground by your own power and manage a safe and controlled flight. But I think that's no worse than the Wright brothers' first flight was, just about the same thing. So it's very good to see you. Thank you very much for coming, Mr. Lassiere. That gives us a point on our curve. We can reckon that the power developed was about 400 watts 300 or 400 watts, and the weight of the all-up weight about 250 pounds or so. And that, between the power, that's about half a horsepower, let's put it that way. 1/2 horsepower, deference to British units, and about 250 pounds. And we can enter those 2 points into our weight curve, and we'll have something to look at when we consider all the scaling problems. Let us look at one of the early petrol-powered flyers. This is a picture of one of the Wright brothers' early flights, which we have recorded, fortunately, on film. It's not the first flight, but one of the early pictures of the Wright Flyer B. A splendid aircraft. Notice the most conspicuous part of that airplane, for me anyhow, it is the engine. And you hear it. The sound of the engine is the sound of the aircraft age, because without the power, it's very difficult to fly. Notice the man to animal relationship. We have a point on the curve, so I can choose which curve I wish. I won't draw it to scale, I needn't, but I say we have got that point. That's where men can fly, but we know, we said before, animals develop power like this is the power developed. The power needed is this curve. The power developed is W to the 0.73, and the two cross at a man's power with a little bit more weight. And this curve, of course, is much flatter. This curve goes up like 1 1/6, 7/6. This curve only goes up like 3/4, 0.73, and so it crosses like this. And as we said before, of course, there's a band allowing for changes in design, little difficulties, but animals heavier than this cannot fly. Animals lighter than this, if they're well and cunningly made, can fly, and that's exactly what we see. The albatross and the pterodactyl, the animals and the man, the 3 flying animals of greatest weight, are all well under 100 kilograms. And I don't think any heavier animal is likely to fly. That's the story. And let us proceed to look then a little bit more closely at the engine which makes flight possible. Could we see an engine? And Daniel, I think we have another engineer to help out. This is a petrol engine. At that corner, a small petrol engine, very similar to the ordinary automobile engine in principle, not exactly, some diesel quality, so-called glow plug engine, very efficient device, which has a tiny volume and uses a very small amount of fuel, but turns up a remarkable amount of power for its weight. Once you start it, it's always hard to start these close-fitting devices. And you must realize that this engine will develop for its weight nearly the same power as the huge aircraft engines that power the big aircraft, of the order of 1.5 or so horsepower per kilogram, in the neighborhood of 1 horsepower per pound. The biggest engines maybe are 2 or 3 times more efficient than that. We'll try to get it started. We've always had difficulty with starting it, so we don't find this surprising. If you try to start your automobile engine on a cold morning, you have the general idea. And these tolerances are much the same. It uses a volatile fuel, which is being put in here and there to prime it and make it work as well as possible. And there's a delicate throttle control, and so it goes. Now you must remember this little engine, which is just about ready to... Oh, split! Yeah. I think we have seen it work, unless you can try starting it a little bit. All right, let's try the larger engine. Thank you, Bill. The little engine develops about 1/30 of a horsepower. Now, a man working in sustained work can develop about 3 or 4 times that. So 3 or 4 of these little engines, these tiny engines, will develop the mechanical power of a very hard-working man. On the other hand, this 10cc engine over there, which Bill is going to try to start for us, is an engine such as used on radio-controlled aircraft, which can fly freely of anyone for hundreds of kilometers, far across the countryside. And that 10cc engine develops nearly 1 horsepower. Again, about 1 horsepower per kilogram is the power to weight. Very good. It will not surprise you Thank you very much, but I thought you were going to take off. It doesn't surprise you very much that an engine like that 10cc model engine develops the power of 3 or 4 men working together. So you see the difference that high temperature and careful engineering design, the work of 300 years of engineering, make. We have power in that little package more than 3 or 4 men. And that's why men can fly, and fly indeed, with the large aircraft. Now, as you came in to your left downstairs, you may have seen what is called a light airplane engine, a real airplane engine. It was so light that we could not carry it upstairs. As you see, it was not very light at all, but it's the kind of engine that might work a 2-place helicopter. And I think we may have a transparency of this. At least we have a photograph. Yes. Here we have a photograph of this excellent engine. It is a beautiful example of technique. Of course, nowadays everything is jet, but we wanted to keep it in the reciprocating engine class so make them as fully comparable as possible. Here you see Mr. Coates himself holding our little 10cc whizzer, and behind it this engine, a Rolls Gypsy Major 215, 215 horsepower and 500 pounds about. Again, you see a couple of pounds per horsepower, 1 kilogram per horsepower. And that's with very advanced engineering, magnesium crankcase, magnesium wheel case, magnesium alloys, everything designed to save weight and conserve power. Thank you. And you see how these things work. Now, you may imagine that as this curve gets bigger and bigger, higher and higher, as the weight goes, the power grows. In fact, the power required goes like a 7/6 power of the weight. The engine power does not seem to go up quite that well. It may or may not, at least this is a question of design, but sufficiently large aircraft require so much power that we don't know how to make them yet. The largest aircraft we have in civilian service today is the VC-10. And here you see this excellent jet, fine jet, which has 4 engines, each one of which weighs about 10 times the weight of the light aircraft engine we have downstairs, which would collapse the floor if we got one of those things in here. And each one, and remember that engine, its turn was 100 times, 200 times heavier than the 10cc model. So you get some feeling of the power that is required to make a big aircraft go. But even that aircraft, if loaded in the following way, with a Brobdingnagian passenger, we've drawn him to scale in the jet, in the VC-10. There he is, lying there, a very uncomfortable cabin passenger, I can assure you. But worse than that, the plane simply can't take off. How many passengers does he weigh in equivalent, if he's a Brobdingnagian? Anybody, you must know. Go ahead.
144.
144? More, I think.
No.
What do you think? What do you think?
1,720.
Yes, nearly 2,000 passengers. Do you know how many passengers the VC-10 can hold to take off? 150 normally. Maybe go to 200, 250, 300 if we overcrowd, but that's the maximum takeoff weight it can sustain. So the machine can't take off with a Brobdingnagian aboard. And that's after a great many years of developing aircraft and aircraft engines. So I think the engineers in Brobdingnag have not yet managed to fly. They probably have model aircraft, splendid model aircraft flying around about this size, but no man-carrying aircraft yet. Thank you. Let us then conclude with if you'll show us the graph, Bill, with a summary of what this means for flight. And I think you will begin to see the feeling of how the scaling has enormously assisted us in the design of aircraft which are powered not by flesh and blood and bone, but aircraft that are in fact powered by engines, the indispensable requirement for manned flight, apart from the heroic efforts of pioneers such as the man we've had the good chance to meet today. Here is here's the man-powered aircraft. I think I have that picture here. No? The man-powered aircraft here, that's the Japanese version, which is a very up-to-date and nifty aircraft. That's about the lightest airplane that can carry a man that's ever flown, in that neighborhood. And here we have another light aircraft. This biplane is an amateur-constructed aircraft called the Botley Curry-Watt. Would you help us by looking up, Peter, some of the data on the Botley I think the page is marked in this fine large book, Jane's Aircraft of the World, which tells us the statistics, nearly all the aircraft. What power does it give? The power in horsepower.
65 horsepower.
65 horsepower. I've entered it about there. And what weight?
900 pounds.
900 pounds. Thank you very much. Right about there. So that's the Botley. I've entered also the Wright Flyer, the Beagle, which is this very convenient and handy commercial aircraft. Can we see the Beagle? And also the Shackleton, just to keep in the propeller-driven aircraft style. This aircraft is, of course, not all that up to date, but it's a very high-performance aircraft for having propellers. That's why I included it. And here we have the curve of the Wright Flyer, the Botley, the Beagle, and the Shackleton, all entered. You see, tolerably on a band, even including this 10cc motor model, such as the kind that they use for radio control. Here's the manned aircraft, and here's the power required on that curve. You see, all of these fellows are way over to the left, and therefore they can fly, because their power exceeds the power required for flight. And in general, the more it succeeds, the better the performance, and that is the story. It's quite remarkable, by the way, that if you do the scaling properly, I seem to learn that we have the scale result that every airplane, no matter what its size, if it lies on a curve like that, has the same range if you fill it full of all the fuel it can hold. It's remarkable to believe that, but I understand that people are hoping in the next few years to have radio-controlled model aircraft a few feet in wingspan with one of those 10cc motors capable of flying the Atlantic Ocean. Hasn't been done yet, but it seems a doable thing. I think we'll have it in the future. Well, of course, the simplest kind of power is spring power, rubber power. The Lilliputians could have had an aircraft like this if they wanted to for a long time. Thank you very much. I think that's very good, and it's still flying. We have a couple of those. Here is another aircraft of foam aircraft of very light construction indeed. Lots of energy, but the body is made of solid of polystyrene foam. That's to say, it's a mixture of air and plastic, but there's no large hollow in it anywhere. No place for man or engine. But this airplane indeed has a considerable capability of flight. The Lilliputians could, of course, have used such rubber-engined aircraft for low-duration flying. The trouble with these aircraft is the duration of flight is very small. Scaling them up makes them capable of flying. If you make them bigger and smaller, they would always fly, but the duration of flight does not depend upon the scale. So if you make a big airplane, it would only fly as these fly for a matter of seconds or minutes, and that's the best we can do without chemical fuel such as the petrol engine. I don't, that's all right. And I think that's about where we ought to conclude. I don't know what the timing is, what has happened to the timing.